friends, welcome to VK Lectures. In this session, we are discussing Bragg's Law and crystallography. Here we are discussing Bragg's Law. Now, if this is the angle theta by which an incident ray makes it with the normal, then this particular point, this one is equal to d sine theta. Similarly, here we have d sine theta, and the path difference, which is given by delta x, will be equal to 2 times d sine theta, 2d sine theta, or the path difference delta x can be written as n times lambda, where n is the order, and this is the Bragg's law in scalar form. And in phase, we can write the change in phase divided by the total phase, that is 2 pi, will be equal to change in the path divided by the total wavelength, or you can write wavelength. This is the equation connecting phase and the change in phase and the change in length. Okay. Now for gratings, we can write it as d sine theta equal to n lambda. Now in vector form, the Bragg's law is written as g square plus 2k dot g equal to 0. So this is the Bragg's law in the vector form. Geometrical structure factor. Now the geometrical structure factor is given by the F. So in direct lattice, we have the parameter R, that is the lattice vector in direct lattice, as R is equal to n1 times vector a1 plus n2 times a2 plus n3 times a3. Okay. Now in the reciprocal lattice vector or reciprocal lattice, we have G is equal to HB1 plus KB2 plus LB3. Now A1 dot B1 is equal to 2 pi into delta Ij, and R dot G is equal to 2 pi times n1h plus n2k plus n3l. And coming to the geometrical structure factor, F is equal to sum over the J value Fj into e to the power I phi j, and phi j is the phase and fj is the atomic structure factor given by, this is fj is atomic structure factor. And what is this phi j phase? Phi j phase is equal to vector r dot g, which is nothing but 2 pi into n1h plus n2k plus n3l. Now there is a note here. In Bragg's lattice, F is constant for every atom. F is constant for every atom. So we can write the geometrical structure factor F is equal to, so this is, we have to write Fj. Okay, Fj. So bring that F out of the summation. So sum over F times sum over e to the power I times r dot g. So that is, so writing the geometrical structure factor F is equal to F times sum over e to the power I r dot g that's equal to F times the sum over j e to the power I times 2 pi into n1h plus n2k plus n3l. So what does it tell you? What does this geometrical structure factor tells you? Now this is the geometrical structure factor F is the sum over all atoms of unit cell. Okay. Now geometrical structure factor, it indicates the reflection from the planes, or it shows the Bragg reflected plane. Now this is how it has been done. Now the intensity is given by intensity of a reflected wave. We want to check whether it is Bragg reflected or not. Now how will you check? By looking at the intensity of the reflected wave. If the intensity is there, it means it is Bragg reflected. If the intensity is 0, it tells you that there is no reflection. So a Bragg plane is not reflected. Okay, so intensity is proportional to the square of the magnitude of the geometrical structure factor. If I equal to 0, it implies no reflection. Okay, if I not equal to 0, it says that planes that we are considering are Bragg reflected. Now going through the simple cubic structure. Simple cubic. Number of atoms is equal to 1, and we can write the number of atoms in this way. This is the structure that we have, and somewhere here you have that particular atom that we are talking about. Okay. So this is at the origin, so this is n1, n2, n3. All values are equal to 0, 0, 0. So at this plane we are checking whether it is Bragg reflected or not. Now if you put the values f as equal to some constant f into sum over j e to the power I 2 pi into n1h plus n2k plus n3l. Now substituting the values of n1, n2 and n3, which is 0, 0, 0, you get the f is equal to simply the constant f, because e to the power 0 is nothing but 1. Okay, and there is only one atom present. So the I, that is the intensity, is equal to the magnitude of f squared, which will be equal to f square, and this is equal to f square for all values of h, k and l. So for all values of h, k and l, I will be equal to f square, which means all planes are Bragg reflected. For simple cubic structure. For simple cubic crystal. For body centered cubic crystal, body centered cubic, we know the number of atoms equal to 2, and volume will be equal to a cube by 2 for primitive units. Okay, now you have the structure. Okay, so one end you have the atom, and another atom would be at the center. So if you consider this as the origin, which is 0, 0 and 0, this point corresponds to 1 by 2, 1 by 2 and 1 by 2. Okay, so this is n1, n2 and n3 for the first atom. This is n1, N2 and N3 for the second atom. Coming to the geometrical structure factor F, so we can write it as F times sum over J e to the power I times 2 pi into N1 H plus N2 K plus N3 L. Introducing the two atoms for J value. For the first point, which is N1, N2, N3 all are 0, you will get F times e to the power 2 pi I into 0 plus F times, for the second atom, e to the power 2 pi I into H. All N1, N2 and N3 are all half, so you can write H plus K plus L times half. Now there are two cases. Case 1 is when H plus K plus L equal to even, or that means when HKL values are even, you get e to the power 2I pi will be equal to 2F. So this will be equal to 0 again. So if HKL values are even, you get F is equal to 2 times F, and that is the case 1. And for case 2 is when H plus K plus L value is odd. If it is odd, then F will be e to the power I pi I will be equal to minus of what we have, so this will become F will be equal to 0. So planes that have H plus K plus L value equal to even are Bragg reflected. Here please make a note that e to the power I theta will be equal to cos theta plus I sin theta. Now as in this case we have e to the power 2 I pi, and here we have e to the power 2 I pi, and this HKL value can be either odd or even, because we know that they are positive whole numbers. So we can write the values of cos theta plus I sin theta as, for example, e to the power 0 equal to 1, e to the power I pi will be equal to minus 1, and e to the power 2I pi will be equal to 1. So that's why we have F is equal to 2 times F here, and in case of HKL being odd, then we have e to the power I pi or 2I pi, which will be odd, so we'll have minus 1. Coming to the FCC crystal, face centered cubic crystal. Here the number of atoms will be equal to 4, and the volume will be equal to A cube by 4. Now here the HKL values must be, if all values are odd or all values are even. Either all values must be odd or all values must be equal to odd. Then your value of f, the geometrical structure factor, will be equal to 4 times f, and the intensity will be equal to 4 times f the squared. Else we have another condition, that if the HKL values are mixed, then f equal to 0. That means the geometrical structure factor is 0. Okay, so which implies that if all values for the face-centered cubic crystal, either they are odd and odd, so it should be, it's not 0, it's odd and odd, or even, then we have Bragg reflected plane. Okay. Now if it is something like odd, even, odd, or any other combination, then it's not Bragg reflected. Lattice plane, we have a different lattice plane. Let us write down the different lattice plane. 1 0 0, where these are HK and L values. 1 1 0, 1 1 1, 2 0 0, and 2 1 0, and 2 1 1, and 2 2 0. And the interplanar separation is 1 by root of h square plus k square plus L square. So we will write 1 divided by root 1, so that's equal to 1, interplanar separation. So 1, here you have 1 by root 2, and here you have 1 by root 3, and here you have 1 by root 4, here you have 1 by root 5, this you have 1 by root 6, and here you have 1 by root of 8. Okay, now coming to the Bragg reflected plane, we have to check for this particular plane in simple cubic whether it is Bragg reflected or not. For simple cubic, we know that all planes are Bragg reflected, so you can put tick for all the planes if in simple cubic as Bragg reflected plane. Now coming to the body centered cubic, for that the sum of the HKL value, so H plus K plus L, should be equal to even for the plane to be Bragg reflected. Okay, so we will check in which all lattice plane we have HKL value, sum of the HKL value equal to even. For the first case, which is 1 0 0, it is not even, so it is not Bragg reflected. And for the second case, 1 1 0, so it is 1 plus 1, 2 plus 0 is considered as even, so 2 plus 0 is again now it's even, so it is Bragg reflected. Coming to the third 111, which is not, the sum is not equal to even. So for the case 200, you have again it is a Bragg reflected plane. For 210 it is not. For 211 it is a Bragg reflected plane, and for 220 is again a Bragg reflected plane. Now coming to the FCC structure, you have the either HKL value must be all odd, or the HKL value must be all, everything should be even. Now coming to the first one, no, the first one is odd, second is even, third is even, so it is not Bragg reflected. Again it is even, odd, odd and even, so it is not Bragg reflected. Odd, odd and odd, so it is a Bragg reflected plane because all values are odd. Now coming to 200, it is again even, 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 so it is Bragg reflected. And this is even, odd, even, so it is not Bragg reflected. And even, odd and odd, so it is not Bragg reflected again. And coming to the last one, 220, all are even, so it is again Bragg reflected. For the practice purpose, you can work on the planes 2, 2, 1 and 2, 2, 2. You can work on this, check whether this is Bragg reflected in simple cubic, body centered cubic and face centered cubic, and also write down their interplanar separation, which is DHKL. And now coming to another note, you have, there is something called h square plus k square plus L square ratio. Now this is h square plus k square plus L square is equal to 1 divided by DHKL whole square. Okay, so this is D and HKL is subscript. Okay, so 1 by DHKL square, so you know, so the square of h square plus k square plus L square. For simple cubic, the ratio h square plus k square plus L square. For Bragg reflected plane, Bragg reflected plane, okay, so ratio is 1:2:3:4, because all planes are Bragg reflected for simple cubic. And coming to the body centered cubic, the ratio goes like this: 2, 4, 6, etc. And for face centered cubic, the ratio goes 3, 4, 8, 12. So these are the square of h square plus k square plus L square ratio of the plane which is Bragg reflected. Now these are, now we'll write there, these are square of 1 divided by DHKL, or h square plus k square plus L square. These are the squares of, these are the square of this particular value, or h square plus k square plus L square, for which the plane is Bragg reflected in simple cubic, body centered cubic and face centered cubic.